Everyone. Today I would like to welcome Dr. Manisha Sharma, who is going to present a webinar on a systematic approach to model development. But before starting the webinar, I would like to give you a brief introduction about ma'am. Ma'am is currently working as an assistant professor in the Department of Chemical Engineering at Manipal University, Jaipur. During the masters, she was awarded the gold medal in chemical engineering from Malviya National Institute of Technology, Jaipur. Soon after completing her PhD in reactive adsorption process, she was also appointed as the first faculty in the Department of Chemical Engineering at Manipal University, Jaipur. Since then, ma'am has been handling the major responsibilities in the department. She has also been associated with the various professional bodies like IICHE, which is Indian Institute of Chemical Engineers. He is the faculty coordinator of IICHE student chapter at Manipal University, Jaipur, and an executive committee member at IICHE Jaipur Regional Center. She also has been associated with Indian Desalination Association and Institute of Engineers, India. The area of research include process modeling simulation, process control and optimization, water and wastewater treatment, and reaction engineering. I would like to hand over the session to ma'am so that we can begin the webinar, and we welcome you, ma'am.
Thank you. Uh, Good afternoon, all of you. And before beginning with the presentation, I would like to thank the entire team of Parallel University for inviting me and giving this opportunity to present a webinar on process modeling and simulation. So, starting with today's webinar, the topic for today's webinar is a systematic approach to model development. And as the title suggests, we would be discussing the basic, the fundamentals and the scheme how to approach to a process development. So first of all, these are the contents where we will be discussing about the role of a chemical engineer in process industry. What is the relevance of modeling and simulation in a chemical industry? Then what are the different types of models available? How to select those models? Depending on the type of equations and the type of mathematical model that we generate from for the given process, then what are the simulation strategies, how the simulation strategies are decided, what are the different kinds of models we will be discussing, and the other steps after the model has been simulated, what are the necessary steps that we need to follow, that we will also discuss over here. Coming to the first thing, role of a chemical engineering. We all are chemical engineers here today, and we all one thing we that comes to a mind of a fresh student that has entered into the chemical engineering is what is the role of chemical engineer. So there are four major roles that a chemical engineer plays in a process industry. First is the design. He is responsible for the designing of any process, any chemical process, any plant, any equipment. He is responsible for forecasting what is the behavior of the process, how the process will behave if any disturbance or any change occurs in the process. A chemical engineer should be able to predict that, and based on his experience, his prediction, he should be able to interpret the results, he should be able to maintain the quality of the product, and accordingly he has to decide the control strategies, how to proceed with the, or how to deal with that change or disturbance. Third major role that is played by a chemical engineer here is optimization. We all know that at the end, money matters. So a role of a chemical engineer again here is to how to maximize the production of an industry, maintaining the quality and minimizing the investment, minimizing the maintenance, minimizing the capital cost and the operating cost. And the last but not the least is how to control the process if any disturbance occurs inside the process. All of a sudden, if any disturbance occurs, then an industry cannot bear up with the, it cannot compromise with the quality of the product. It has to maintain the quality of product, and there the role of chemical engineer comes into picture, where he has to be proactive in deciding what, in predicting how the quality will be affected if any change occurs in the plant. So immediately he has to take an action, and he has to control that the quality of the product, or to minimize that disturbance. So for all these things, what he must know at the end of his chemical engineering, he should be aware of the basic fundamentals. While working in industry, whatever plant he's dealing with, he should be aware of the background of the process. He should know every in and out of the process. He should be aware if how the process will behave if any change is occurring in the process. So how he does that, there are two different ways. One is the experimental way, another one is a theoretical way. So we will be discussing one by one. Experimentally, he will behave, how he will predict the behavior of a plant. In prior, he has to conduct certain experiments, or he must have the set of experimental data under different conditions, and based on that data he has to analyze the result. He has to see, okay, if this change is occurring, if the flow rate is changing, then the quality is affecting by this much percentage. If some other parameter is changing in the process, then how the end product quality will affect, or how the process will behave. That means he should be aware of the fundamentals of the process that he will gain from chemical engineering study, and in the plant he should be aware of every in and out of the process. Now, to conduct the experimental data and to generate the experimental to conduct the experiments and to generate the experimental data, it is a very time consuming process. Also, it requires high operational cost, high manpower is involved, and it requires a lot of effort, lot of time. So to avoid all these things, we have option modeling and simulation. Once we know every in and out of the process, we can transform that process into a set of mathematical equations. We can program that, or we can develop that mathematical model, and we can see, validate that model with the available experimental results, and we can predict if any parameter is changing, what will be the behavior of the process based on the mathematical equations. Right. So this second approach, that is the modeling and simulation, is the most preferred approach, as it is less time consuming. It requires very minimum amount of experimental data, and it requires less efforts. So what is mathematical model, or what is modeling means? In engineering, we mean by model that we are representing the process, entire process, or we are representing the equipment of a given process in terms of mathematical equations. So using that mathematical equations, we have to we can develop a model, and we can simulate it, and then we can predict its behavior, and accordingly we can decide the control strategy. So first thing is, we need to have an understanding of the process. Once we have a proper understanding of the process, then we can transform that process into a set of mathematical equations. After the set is generated of mathematical equations, we can analyze which type of mathematical equations are involved, and accordingly we can decide upon the simulation strategy to solve that mathematical model. Then the results are obtained out of it. We analyze those results, and we can predict the behavior of the plant. And based on the result analysis, we can we can give our inputs, and we can improve the further performance of the plant. But one thing we need to remember is the model that we have developed is not a perfect alternative to a real life processes, because every mathematical model, it is an imitation of reality, but every mathematical model is based on certain assumptions. However, a plant, it doesn't work on assumptions. It encounters the real scenario, and our mathematical model we have to take certain assumptions. Slowly and gradually we can evolve that mathematical model by removing one assumption at a time, and we can validate our results with the real plant. Applications of a model where it is required. As we have already discussed, that one of the major role of a process engineer is designing a process. Here the mathematical model is very much relevant, because based on the process knowledge, if we have the information about the process, if we know what are the chemical reactions are involved, what is the kinetics of the process, we can develop a mathematical model for it, and we can predict its performance, and we can judge whether this process is relevant for an industry or not. Training an operator is the second application of mathematical model. Rather than giving an hands-on practice on the plant every time, we can give the mathematical model to an operator and we can provide them training. They can We can give them an overview of the process, and then after they are properly trained, we can deploy them in an industry, so that they can be well aware of that system and they can perform efficiently. Controlling the process, we have already discussed. If any disturbances occurred, we can put that disturbance into the mathematical model and we can generate the output of the system, and accordingly we can decide upon the process control strategy. Troubleshooting, what if anything goes wrong? Immediately we can use our mathematical model and we can look into it, where the problem is and how can it can be removed. Environmental impact, like the emissions and all those things, we can calculate. And last is the but not the least, that is very much important in the chemical industry, is the process safety. So mathematical models are also employed there to ensure the process safety. Different types of mathematical models are present here. Mechanistic models are there. Mechanistic models are generated if we know every in and out of the process. We know everything about that process, every mechanism is known to us, then the model that we have generated is known as the mechanistic model. Empirical model is the model which is applicable for certain conditions. Okay, like we have some experimental data which is generated under certain set of conditions, and using that experimental data we can generate the mathematical model which is applicable within that range, particular range only. That model is known as empirical model. Other type of models are stochastic model, which are the probabilistic model, we can say. We can predict the most probable result, the, or the behavior of a plant. Deterministic model is there, where we are very much sure, which will give you the surety results, like what will happen or how will the process will behave under different conditions. Lumped parameter and distributed parameters. Lump parameter model is in which we generally do not consider the spatial variations. However, in distributed parameters, we do consider the spatial variations. So based on this lumped and distributed parameters, which we will be going to discuss in some detail in the coming slides. So we can like lumped parameter and distributed parameters. Both these models will contain different set of equations, and accordingly the simulation strategy will be decided. Other type of models are linear models, which are based on the type of mathematical equations that we are getting. Non-linear models, continuous models, discrete models, and a combination of different models is the hybrid model. So this is the hybrid model which we generally encounter in industries. We get a combination of linear equations, we get a combination of non-linear equations, differential equations, which can be ordinary or partial differential equations. So we get a set of different types of mathematical equations. So that is known as the hybrid model. So in industry we generally encounter the hybrid models. So here we will start with the development of a process model. So we should be aware of the fundamentals of process modeling. So these are the two extreme process models that we can develop. One is a model which is having a single input and a single output. Second process is a process in which we have multiple inputs and multiple outputs. Other type of models will lie between these range. We can have a single input, multiple output model. We can have a multiple input and single output model. So these are the two extremes, CISO and MIMO systems, that we encounter in chemical processes. So we will learn how what are the different steps involved. So one thing is you should be aware of the behavior of, or the we should be aware of the process, what's exactly happening inside the process. Kinetics should be known to us, right? So once all these basic information is obtained, then we have to follow the 7 basic steps involved in the development of process modeling. First thing is problem description. We should be aware for which problem or which process we are developing the model. What are the controlling factors involved? Then we evaluate the problem data. We do some brainstorming. Okay, what is the problem? How we can approach to this problem? After we have uh, identified what are the different variables involved, how many equations or what are the different equations that we can develop, then we will start with the process of model development. After the model is developed, after a set of mathematical equations are obtained, we simulate that process. Simulation means we are going to solve that set of mathematical equations, and we can generate the desired result. So once it has been solved, now we have to identify, we have to be ascertain, or we have to be assured whether the developed model is correct or not. There comes the verification and validation part. So based on the experimental data that we have in prior with us, we will be validating our model, whether it is giving us the same result as we are getting with the actual process or not. If not, again you have to do some rectification in your model, and again simulate it, again validate it, again verify it. After it has been validated with different under different conditions with different experimental data, then we are pretty much sure that this is the model that represents our plant or that represents our equipment, and we can use that model for future purposes. So here you can see that there are 3 different models: white box model, black box model, and the gray box model. White box model means everything is transparent, we know everything about the system. Black box model is we do not know anything about the system, we just have a set of experimental data, and based on that experimental data we have to generate our model. That we often do in curve fitting. We just have the set of experimental data and we fit that curve to predict the behavior of that process, right? So that is a black box model. Gray box model means we know some fundamentals, we know some kinetics, some data is available to us, some process description is available to us. So that is a sort of a gray box model. Something is known, something is not known, right? So we can develop it is very easy to develop a white box model. It is relatively difficult to generate a gray box model. Black box model is again a predictive model which is based on certain set of experimental data, and we can predict the behavior of a plant under that conditions. So these are the 7 steps of modeling that we need to follow. Coming to the different models, dynamic and steady state models. By dynamic, we mean that the conditions are changing with time. Steady state means the conditions are not changing with time. So we have different models, lumped parameter and distributed parameters. The overview I have already given to you. So in case of lumped parameter dynamic models, we are assuming that these spatial variations are not present over here. So if the spatial variations are not present, that means the parameters are changing only with respect to time. So there we will get the ordinary differential equations accompanied with the initial conditions and the some algebraic equations that we often call them as constitutive relations. So we get a set of ordinary differential equation, we have initial conditions, and a set of constitutive relations. So this set is known as differential and algebraic equations, or the DAE equations. Second is the distributed parameter dynamic models, in which we also consider that the parameters are not only varying with respect to time, but also they are varying with respect to space. For example, if we have a reactor, so if it is properly agitated, then the concentration of the reactant or the product is uniform throughout that reactor. In that case, we can assume that the concentration is same throughout, and we can go for lumped parameter model. However, in case of if the mixing is improper, then different zones will be formed inside that reactor. Temperature zones, hot zones will be formed. In terms of concentration at different point will be different. That means the concentration is changing with time because reaction is happening over there. So as the reaction proceeds with time, more and more product will be formed. So concentration will change with time. So at the same time, the concentration is also different at different places. So it is also changing with space. So there we get partial differential equations because our parameter, let's say temperature or concentration, it is changing partially dependent on space, coordinates, and it is also changing with time. So we get partial differential equations with a set of some initial conditions and the boundary conditions. So here we get a set of partial differential equations. So here we are getting two different models, distributed parameter models, where we get the partial differential equations, and lumped parameter models, where we get the ordinary differential equations if the model is a dynamic model. Coming to the next type of model is the steady state model, where the parameter values, they do not change with time. We assume that now the parameters are pretty much constant. So again, lumped parameter dynamic model, we had already discussed that we get a sort of ordinary differential algebraic equations. Now in ODE, if we are talking about ODE and we are saying that we are talking about the steady state models, in that case, with respect to time, there is no change in the value of that parameter. That means the time derivative is dx by dt, it is zero. If it is zero, then ordinary differential equations are gradually converted into simple algebraic equation. So here, assuming the steady state, taking the steady state assumption, we have converted the ordinary differential equations into a set of algebraic equation, and accordingly we can decide the simulation strategies. So here we can have seen that based on the assumptions, based on the characteristics of the parameters or the characteristics of the process, we can have algebraic equation that can be linear or non-linear. We can have the ordinary differential equations with initial conditions, and we can also have partial differential equations with some initial conditions and boundary conditions. So basically, we have four types of equations that we encounter. Algebraic mein, there is linear, non-linear equations, then we have ordinary, and then we have partial differential equations. In case of distributed parameter dynamic models, we had a set of partial differential equations. Now, if we are assuming that we have a steady state model, that means the time derivative is zero. So partial differential equations can be reduced to the ordinary differential equations along with the boundary value problem. So such type of equations are known as ODE-BVP, ordinary differential equations with a set of boundary conditions. So different sets will have different simulation strategies. We already discussed lumped parameter, no spatial variation is there. Model equations are developed for every operating unit, every phase, every component. And again, overall mass and energy balance equations are involved. We all know that chemical engineering is nothing but it is all about mass and energy balances. Okay, so we will start with the model development. First step is to identify the process. We should be aware of the description of the process. For that, we have to identify our system. We should be well aware of the system boundary and the system itself. So here we use two different terms in modeling and model development. One is the control surface, and the second one is the control volume. Control surface is nothing but the boundary, and control volume is the system that we will consider for our model development. After we have identified the system, we have identified, marked the system boundary, then comes what all parameters are involved, what are the variables that are involved. So there are two different variables, two types of different variables. One is the fundamental dependent variable. These are the variables whose value is known at any time and they contain all information about the process. The basic variables are mass, energy, and momentum. This is all about chemical engineering deals with mass balances, energy balances, and momentum balances. Second variables are the characterizing dependent variables. These are the variables which can be measured very easily and they can be clubbed together, and the fundamental variables can be identified or can be calculated. For example, using the density and volume, we can calculate the mass, temperature, pressure, flow rate, etc. They can be calculated. Often they are also known as the state variables. So state variables are density, temperature, pressure, flow rates. These can be combined together to identify the mass, energy, and momentum. Once the variables are identified, we start developing the mathematical equations, which, as I've already mentioned, that they are based on the mass balances, energy balances, and momentum balances. So overall, we can say that they are based on the principles of conservation. And principles of conservation states that for any extensive quantity, whatever is going into the system must be related with the process output. If anything is generated, then we have to add. If there is no generation, then whatever is going into the system, it should be related with the output of the process. And the basic statement for principles of conservation is flow in through the system boundary minus flow out plus net generation minus net consumption is equal to the change in the quantity with time. In case of steady state model, the last term, that is the net change in quantity with time, will be equated to zero, and you are left with flow in through boundary, flow out through boundary, and net generation or consumption. So this is the basic principle of conservation statement on which the three different balances, mass, momentum, and energy, are based upon. The common mass balance. So we deal with the systems having two or more components. So there are two types of mass balances involved. One is the overall mass balance, which is applied to the entire system, which says that the total amount of the material going into the system minus the mass flow out from the system is equal to the net rate of accumulation. Second is the component mass balance, where we need to apply mass balance for individual components. So there are cases where the components are consumed, where the components are generated for reacting systems. Then the general mass balance equation is represented as mass flow in minus mass flow out plus rate of generation minus rate of consumption is equal to rate of accumulation. So these are the two basic mass balance equations. Same goes with the energy and momentum balance. So these are the simple statements or the simple expressions for energy balances and momentum balances. So these three balances are utilized to develop the mathematical model. Here is an example of an evaporation system. Now there are two basic, if you want to design a mathematical model for it, there are two basic possibilities. One is if we had taken the entire evaporator as our system And what we have two phases in the evaporator, one is liquid and another one is vapor phase, but we have assumed it to behave as a single phase. In that case, lumped parameter model will be available for to us. However, if we have taken vapor phase as one system, liquid phase as another system, and the heating element as a third system, and we have developed individual mathematical expressions for that, then in that case, for individual region, we will be developing the lumped parameter models. So depending on the type of process that we are dealing, this is for the non-reacting system. If reaction is occurring, then obviously you have to go for the distributed parameter system, particularly if this process is non-isothermal. So here, a simple example I have mentioned here. We have a tank filled with a liquid up to a certain height, H naught, and an orifice is provided at the bottom of the tank. Area of orifice is constant, kept constant at A naught. Cross-sectional area of the tank is A, density is rho. So if I want to develop a simple mathematical model, if I want to express this process in terms of mathematical equations, then we have to consider there is no input stream to the process. So input stream will be equal to 0. Now coming to the output stream. So we have a process here. The equation will be mass flow in minus mass flow out is equal to rate of accumulation. So since there is no mass flow in, this term will be 0. We are left with minus mass flow out is equal to rate of accumulation. So what is the amount that is coming out from the system? We have, let's say, m mass of the fluid that is coming out from the orifice is m. We know what is the flow rate. Okay, we can multiply it with the density. So we will get the rate of mass flow out from the system. Negative sign means it is coming out from the system. Is equal to rate of accumulation. How much amount of fluid is present in the tank? So right hand side equation will be rho into A into H. That means density into multiplied by volume will give you mass, and dividing it by the time, rate of change of accumulation will be obtained. Okay, so we have expressed it in the terms of differential form. Del of mass divided by the change in time. So because the fluid is continuously flowing out from the system, that means the amount of liquid in the tank will change with time. So rate of accumulation we are representing in terms of differential equation. Now, based as I have already said that the equations or the mathematical model is based on certain assumptions. So here we have assumed that the density of the fluid remains constant throughout. If the density of fluid is constant, if the area of cross section of the tank is constant, then this rho into A term is taken out from the differential term and equation is further simplified. So density terms will get cancelled out and we are left with minus Q by A is equal to dH by dt. So this is the sole mathematical equation that represents the behavior of the plant. Now, how to solve this? Before that, we need to do the degree of freedom analysis. Here you can see that there are two variables involved. A is constant. Q is the volumetric flow rate of the fluid. Now, as the height inside the tank changes, pressure will vary, and accordingly, the flow rate will also change. So Q is a variable here, H is variable here. We have two variables, one equation. We cannot solve this equation directly. We need one more relation to make the degree of freedom 0. Right? Now we know that as the height is changing, Q is changing. As the pressure is changing, Q is changing. So we can relate flow rate with height, we can relate flow rate with pressure. So that means flow rate is a function of pressure, change in pressure, and flow rate is also a function of height. So we can represent this relation in terms of simple algebraic equation, and that equation, additional equation, which is required to make the freedom of degrees of freedom equal to 0, That relation is known as constitutive relation. So the differential equation plus a constitutive relation completes our mathematical model, right? So this is how the mathematical model is developed. Simple steps that we had followed are understanding the process, physical situation, what are the variables that we need to consider, identify those variables, whether they are fundamental or characterizing, then apply the conservation principles and develop the basic model equations, go for the degree of freedom analysis, check whether we have enough number of variables and enough number of equations. If not, use the constitutive relations, make the degree of freedom 0, and then simulate that mathematical model. Right? So these are the basic steps. We had discussed the 7 steps of mathematical modeling, and here are the basic steps of model development. How to proceed with the model if the process is known to us. So basic structure of process model is assumptions, fundamental and characterizing variables, development of the model equations, identifying the constitutive relations. If we are getting the differential equations, then we need to also identify what are the initial conditions, what are the boundary conditions, and the parameters involved in the process development. So this we have already discussed. For continuous process also, we can develop the model. So here we have an input stream and an output stream. So based on the conservation principles, we can develop the mathematical model for the given process, and then we can simulate it. So mass of fluid in tank at any time is given as density into volume. After a certain time period, it is let's say after delta t time, the mass of fluid that is entering in the tank between the time t and delta t is rho into q into delta t. So similarly, we can write down the expressions for individual term involved in the conservation equations, and then we can generate the overall balance equations. So here is the overall overall mathematical model for the given process, where height is changing with time. Initial height is known to us, so we have substituted the initial height as h naught, and then the expression that relates the time and the flow rate. So this is how the mathematical models are generated for different processes. Similarly, for the reacting systems, we have incorporated one more term, that is Ra into V, that represents the reaction term. How R is related? It is related with a constitutive relation. So for this continuous stirred tank reactor, we need to analyze how the concentration of the reactant are changing and how the concentration of the product is changing. So we have a set of equations representing the overall mass balance. The first equation is the overall mass balance, the amount of reactants going into the system minus the amount of material coming out from the system is equal to net rate of accumulation. This is the overall mass balance. Then we are dealing with two or three different components. So we have to take into consideration the component balance as well. So these three equations represent how the concentration of an individual component is changing. Also, the reactants are undergoing some reaction, so we have involved the reaction term as well. Now, how these reaction terms are related with the overall rate equation? So based on the stoichiometric analysis, we can use the relation, we can develop the constitutive relation that would relate the individual rate of reaction with the overall rate of reaction. I'm not going into the details of reactions because this is related to the chemical reaction engineering, and if I discuss it here, it would consume a lot of time. But I'm assuming that the students are well aware of the reaction engineering as before developing the mathematical model for reacting systems. We can simplify these models, and we can generate a set of differential equations. So here we have 4 differential equations and 1 constitutive relations, and accordingly we can do the degree of freedom analysis and solve it. For steady state also, we can remove the differential terms and we will get a set of algebraic equations. This is an example, a complex example of a process. Till now we had seen the examples for individual equipment. Here is the overall equations mathematical model depicting the evaporator system. We have a feed stream. We need to concentrate that feed stream. We are feeding this feed stream into an evaporator. Steam is used as a heating source. Now, the inside that evaporator, the feed stream will be heated. It will get vaporized. The output stream is sent to a condenser or a separator, where we will get 2 different streams. One stream, that is the liquid stream, will be rich in the desired component, and the vapor stream, it is taken out from the system. It is sent to a condenser and collected. Also, the liquid stream is half of the some part of the liquid stream is taken out as a product stream. That is, X2 is the desired component here, and the part is recycled back to the evaporator. So for this system, this process, I have assumed that evaporator plus a separator is the system. So for this system, these are the set of mathematical equations based on the conservation principles. Here we have seen the variation of liquid level in the separator with respect to time, variation of the composition with respect to time, and variation of the pressure with respect to time. So these are the 3 basic equations accompanied with certain constitutive relations. So here we are having a differential algebraic equations. Now, how to solve? Degree of freedom analysis says that we have total number of variables 20, total number of equations 12. That means we need degree of freedom is equal to 8. That means we need to specify the value of 8 more variables, so that degree of freedom will become 0 and we can further solve that system. Right? So these are the basic parameters that are available to us. So based on the degree of freedom analysis, we have identified that these are the 8 different parameters whose values need to be specified. So here we have specified those values. Coming to the solution, this is all about the model development. Once the mathematical model is developed, we need to simulate it. We need to solve that mathematical model. So finding a solution strategy, as I have already mentioned, that we deal with different 4 basic equations: linear, nonlinear algebraic equations, and differential equations. So based on those, we can go for the analytical solution. We can solve these equations mathematically. Also, we can go for numerical method, which is a more convenient approach. So for linear algebraic equations, this is Gauss elimination is the most common method. For nonlinear algebraic equation, we go for Newton-Raphson methods. Ordinary differential equations are solved with the help of Runge-Kutta, and partial differential equations, we solve it using the finite difference method. These are the general. Other methods are also available, and numerical method is the most commonly employed in chemical engineering because it requires the least effort. Computational methods are present over here. We can use the computers to solve these equations. Different solvers, different softwares are available, like MATLAB is there, Aspen is there. So you can just in MATLAB you can just do the programming and you can use an appropriate solver to solve this equation. For evaporator, we have differential algebraic equation. So there are 4 different methods to solve. Either you substitute the algebraic equations into ordinary differential equation and you can solve it using an ODE solver. Second method is solving the algebraic equation simultaneously and then you calculate the derivative equations. Third is sequentially solving the algebraic equations and using the derivatives. And the last method that is involved in the simulation is the DAE solver. DAE solver is commonly available in the softwares. So you can directly deploy the DAE solver to solve these equations. So once you have simulated the model, you will get the results either in the form of numerical values or in the form of graphical. So for this evaporator system, this is the first graph. It shows the steady state result. You can see that nothing is changed with respect to time. That means the process is operating at steady state. No disturbance is there. Using this using this mathematical model, we can predict what will happen if certain disturbance is occurring in the system or some conditions are changed. For example, if the inlet concentration of the desired product is increased by 20% in the feed stream after 20 minutes, all of a sudden, right, how the system will behave. If the inlet concentration of the desired product is increased, obviously at the outlet the composition will increase. Sorry. So this is the green colored curve indicates after 20 minutes the output concentration has started changing, and after 60, around 60 minutes, the concentration has become constant. So we can predict if 20% is in changes there, how the output concentration will change. How the Similarly we can predict how the level of the separator can change, because we need to control the level of the separator. Pressure, how the pressure will change. Okay, we are getting two different phases. One is liquid phase, another one is vapor phase. So how that pressure is changing, we can also see with the help of this model results. There are different cases involved, like what if the concentration is decreased, what the steam supply is increased or decreased. So these are the results that will reflect. Here, if the steam supply is increased, there is no effect on the output concentration. We know whatever it will not affect the concentration of the output stream, but it will affect the level of separator and the pressure. Because more the steam will supplied, more will be the evaporation. So it will affect the pressure and level of liquid inside the separator. This is how you predict what will happen if any change in the system is occurring. After it is simulated, we need to, one step is missing over here, we need to validate our model. We have the experimental data. We can check under what conditions are we getting the desired results or not. That here comes the verification and validation. And the validated model we can use for future prediction. So this was all about the modeling and simulation. Uh, Other things I also wanted to discuss, but I think the time is not allowing me to discuss all those things. I'll quickly go with the dynamic models. So dynamic models generally encounter in case of the reactions where the concentration is changing with space, where the concentration is also changing with time. The common example here is reaction and diffusion in a spherical catalyst particle. So these are the equations here we have expressed in the form of dimensionless model. And we can see that here we are getting the differential equations along with some initial conditions and boundary conditions. So we have to use finite difference method to solve. Applying this finite difference method, we can reduce the partial differential equations into a set of ordinary differential equations, and we can use the ODE solver to solve that equations. So solving this mathematical equations, we can generate the concentration profile, what is happening inside the catalyst. Another example, I will not go into the details, is the adsorption column. So these are the set of equations, based on certain assumptions. These are the equations. These are the constitutive relations, the certain set of conditions that are already available with us. And this is the validation part. The dotted data represents experimental data, and the lines represent the results generated obtained from the mathematical model. And here we can see that the experimental data is closely matching with the predicted results. After that, we can do the whatever we can play with the model and do whatever we want to do. We can analyze the different effects. What if the bed height is changed? What if the initial flow rate or initial concentration is changed? So once it has been validated properly, then we can say that yes, our model is ready, and we can keep it for future analysis. What if anything goes wrong in the system? We can easily predict using the mathematical model what will the possibility, what are the changes, how the system will behave, and then accordingly we can decide upon the uh, control strategies. So this was all about the basics of the process modeling and simulation. And I hope that it has given you an overview how to um, proceed with the development of a mathematical model. That's all from my side. Any questions?
Yes, thank you so much, ma'am, for your valuable time and providing us with the basic introduction about modeling and simulation. I have got a few queries from the students.
Yeah.
Uh, One of the queries is that what is the uh, significance of black box and gray box approach, that where in which case which in we can use this approach like black box and the gray box.
Okay. There are three types of models. One is the white box model. White box means everything is transparent to us. Everything we know about the process. We have certain experimental results. We also know the kinetics. We also know the exact mechanism of the process. So if we have everything with us, available with us, it's easy to develop the mathematical model for that. Second is the black box model, where we don't know what is the process all about. We just have the set of experimental data with us. Okay, we don't know what is actually happening inside the process, or on what mechanism the process is occurring. So based on that experimental data, we try to fit that experimental data onto a curve. We generate the equation of that curve. That is the mathematical equation that represents the behavior of the process, like what we do in generally we do in curve fitting process. Kinetics, to evaluate the kinetics of a process, we have the experimental data, concentration, time data. We use that data, we fit that experimental data, we fit that trend line, or the best fitted curve we determine, try to get the mathematical representation of that best fitted curve. So that is the uh, black box model. Gray box model is we know something about the process, we know few of the mechanisms, and we also have the experimental data. So certain mathematical equations we can evolve, use the basic fundamental equations, and we also use the experimental data to develop the mathematical model. So that is a gray box model, where we know some mechanism, not the entire process or not the entire mechanism, but we know something about that process. So that is a gray box model.
Okay, thank you for providing this clarification about the significance of this model approaches. And one more query is that since we know we have Aspen HYSYS and CFD, then we have ANSYS, and, and and MATLAB as well. So which software would be like most suitable for using modeling and simulation, or even developing a model?
Okay. In industries, if you are talking about industries generally have a well-built software. They use the CFD Fluent, and they
Yes.
also use the Aspen HYSYS. But if the exact mechanism is available to us, then we can code that, and every process, every simulator available is based on the coding. Initially, we do the coding, and then we can provide the user interface to the user who is using that. So if we are talking about HYSYS, if you're aware about the Aspen and the HYSYS, we have certain user interface. We just have icons displayed on the screen.
Yes.
Based on the process, we just drag and drop that icon. But on what principle that icon is working? Again, the mathematical model is behind this, that icon. So the engineers have already programmed it and provided a user interface to the students or to the user, and they can directly use that. Regarding the preference, I would again prefer to go with the coding procedure, because I know what is behind that process, so I can easily play with that model and do the necessary manipulations in that.
Yes, very correct. Because in that case, coding will be based upon our own method, so we will know that in case we have some error or just want to, if we desire a particular change that we can do by the coding.
Exactly.
And then there's one last question that in the mathematical model, how does the degree of freedom come into the picture and how does it help in solving the problem?
Okay. Degree of freedom is very much important in solving the mathematical model, because we have a number of equations involved, we have number of variables involved in that. So taking a simple example, if we have two equations and two variables, two algebraic equations and two variables, we can easily solve those equations simultaneously. But what will happen if I have one equation and two variables? I cannot solve it directly. I need one more information about that system to solve that. So here degrees of freedom comes into picture. We generally we just subtract the number of equations and number of variables available. So if I say that degree of freedom is 3, that means I need to specify 3 more variables in order to make that system solvable. If degree of freedom is positive, that means something is lacking. So we need to supply more information. We need to have more information to solve that model. If degree of freedom is negative, that means our system is we have supplied the extra information to that system. So we have to remove that. The thing is, we have to make the degree of freedom 0 to solve that mathematical process. So here the constitutive relations come into picture. We have added like if the degree of freedom is 3, so we have to supply either the numerical values or we should relate those 3 parameters with each other so that degree of freedom can be reduced to 0.
Yes, ma'am. This voices the clarification of the importance of the role of degree of freedom.
Yeah.
So those were all the questions which I had. So I would again like to thank you for your precious time and sharing the knowledge with us. And this session has been very informative, and it has really provided us with the very nice way of basic understanding about the model approach and what are the different equations which we use. So it was really a very informative session. Thank you so much, ma'am, from the Power University and from the chemical department, from the chemical engineering department.
Thank you, thank you. I'll again thank all the entire team of Parul University, and especially Mr. Shubham Bartwal for coordinating this event. And very well, you have managed this event. And I hope that students are benefited from this, especially the second year students who have just entered in chemical engineering. So the role of chemical engineering in process industries is pretty much like, I can hope that it's now clear to all those students. Thank you.
Yeah, sorry, ma'am, I just lost my internet connection.
Ah, it's okay.
Okay, ma'am, we will conclude the session here. Thank you so much
Okay, thank
for
you.
this wonderful session.
Thank you.
Thank you, ma'am.
Bye. Take care.
Okay, bye. Yeah, welcome. Hello, sir. We can end this session. I'm also leaving.